fact, I do want to go over this quiz. The grades on this quiz were about 10 points lower than usual. And I'm actually okay with that, in as much as you guys did a lot of really good work here, but there were a number of small things that need cleaning up. So that's about right. Everybody ends up with more or less B's and C's on small things that need cleaning up. That's appropriate. So write a 4 rectangle left sum that estimates, do not evaluate. Some of you did the hard work of writing out in some form. That was absolutely not necessary. All that we need is a delta x is equal to b minus a over n, and my n is 4. Some of you left n as n. That 4 rectangle thing right there is telling you the value of n. And my xi is going to be equal to 1 plus half I. And now I want a left sum, so I'm going to choose xi minus 1 as each one of my x's. And I can do that manually. My first one is going to be 1. My second one is going to be 1.5. My third one is going to be 2. And my last one is going to be 2.5. And I just need to give this as a square root. And then I'm done. And that's it. So the place, yes. Oh, did you not get your quiz? I graded it. Kept it. There you go. So are there questions on that one? Please notice that if you have a small number of rectangles, writing your sum in unrolled form makes a whole lot more sense than writing it in rolled up form. You could, if you had wanted to, write it out as the sum from I equals 1 to n of the square root of 1 plus I minus 1 over 4, but n is 4. So this is a perfectly acceptable way of writing it also, but it's a lot more but it's a lot more cumbersome, I think, than just writing it in unrolled. I borrowed this term, unrolled form, from computer science. In computer science, you can write code, do something in a loop, and then if that loop is for some reason being really slow, then you can take and unroll it so that you do boom, 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 boom computations right away. Questions, comments, jokes? Okay, the next part made me really, really happy because almost all of you got this right. We're looking for this guy right here, and this was the hard question on the quiz, and so most of you did this very expertly. We have delta x is going to be equal to 3 over n, and x of I is going to be 0 plus I times 3 over n as my partition. And now it makes sense for me to do a right-hand sum so that ci is going to be equal to xi. And so a Riemann sum is going to be the sum from I equals 1 to n of fci plus I 3 over n times the delta x, just like that. And there's my setup. The setup was the hard part. If you got this far, most of you carry this home just fine. And now we simplify that, getting the sum from I equals 1 to n of 27 I squared over n cubed plus 9 I over n squared. Turns out to be 27 over n cubed times the famous n times n plus 1 times 2n plus 1 over 6 plus the famous over 2. I thought you guys might appreciate having the formulas at the top there. And now I'm going to take the limit as n goes to infinity as a way of forcing my mesh size to go to 0. And that's going to give me 27 times 2 over 6 plus 9 times 1 over 2. And that turns out to be equal to 13 . Oh, good. Yeah, we're almost there. Now, we've got a velocity of a lab cart measured while it undergoes collision. UAP physics students, does that seem like reasonable data for your velocities? I was happy with that chart. Use a midpoint sum. The only thing that bugs me about it, well, may just be a function of when we measure it. Yeah, okay, I like this thing. Use a midpoint sum with 4 rectangles to estimate the velocity, the integral velocity from 0 to 0.8 dt. And because I'm using a midpoint sum with 4 rectangles, then I'm going to go, I'm not going to go ahead and, I'm not going to put the data up. But what you wanted to do was to select the midpoint of each interval. And the midpoint of the first interval is 0.1 times the delta t, plus the midpoint of the next interval is 0.3 times your delta t, 5 times your delta t, 7 times your delta t. Midpoint sums are really interesting because for a given number of rectangles, they are generally more accurate than either the right or the left-hand sum. But if I have n data points, I can only get half as many midpoint rectangles out of the given data points as I can from left and right. So this interesting compromise in accuracy between the two. And now when you actually add up the numbers, what you get is 3 times 0.2 plus 2 times 0.2 plus negative 0.8 times 0.2 plus negative 2 times 0.2. And all that adds up to 0.44 meters. Just like so. Yes?
When we were learning about midpoint sums, and you said CI equals xi plus xi minus 1 divided by 2.
Yep.
What is that?
Okay. So let's actually get our data table up here. This is part of it. Try it again. Okay. Now, since I'm doing a midpoint sum with 4 rectangles, that means that my partition is going to go out to 0.8, like that, okay? And so, pick an I between 1 and 4. Between 1 and 4. What's that?
Maybe 4.
Pick an I between 1 and 4. Good. Okay, so I equals 2. Here's I equals 1, I equals 2, I equals 3, I equals 4, just like that. And x sub I is going to be x sub 2, and x sub I minus 1 is going to be x sub 1. So, according to the formula, CI is equal to xi plus xi minus 1 over 2. That should be then x2 plus x1 over 2, which is 0.4 plus 0.2 over 2, which is exactly 0.3. There's C2 right there. It is the midpoint of the interval xi minus 1 to xi. Does that help? A lot of what's going on is that you guys are just figuring out what the language means, little thin pieces of things. And that's totally cool. That's appropriate. That's where we are. Okay, now the fun question. Using correct units, explain the meaning of the integral of velocity dt. Three closely related terms in motion. Position, displacement, and distance. These are often used interchangeably because under many circumstances they happen to be numerically equal. Under other circumstances, not so much. So, position is where you are. It is your current location. You dial in the headquarters and they say, what's your position? And you're not going to tell them, I've traveled 20 miles. You're going to tell them, I am 4 miles north of blah, 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 and 2 miles east of blah, blah, blah. You're going to do the GPS coordinates. Okay? So these are coordinates. It's where you are. On a number line, if I'm moving along a number line, it presupposes that I've got an origin somewhere, and I go out to some location, and there I am, there's my S of t. There is no sense of motion associated with position. It's just where you are at that point. Those of you who gave me that the integral of velocity was the position were implying that the particle started at x equals 0 or s equals 0. But that's not actually given in the problem. You don't actually know that. See what I mean? Does that make sense why it's half off? Yeah? Okay. Now, displacement is closely related to this. It is the change in position. The displacement is how much your position has changed by. So, if my object goes forward to 2, and then it comes back to -3, like so, then the displacement is simply final minus initial, which would be -3 minus 0 is -3. That's it. The displacement is just the sign difference between where you started, or where you ended up, and where you started. It does not know or care how you got there. This is what the integral of velocity computes. How do I know this? Well, because what the integral is computing is the net sign accumulation of rate. So if the velocity is positive, then it's accumulating positive displacement. If the velocity is negative, it's accumulating negative displacement. When you add all that up, you're getting the net sign change in position. Does that make sense? So the correct answer to this question is, we want to phrase it like this. Is the displacement, or you could say net change in position, of the object in meters for So this is actually official language, and you want to make sure that you know how to use the official language, so watch this language carefully. Okay? There's 3 pieces about it. The first was, I definitely had to give the right units because the problem said so. And the second was that I needed to give a specific time interval, because without that time interval, I am not accurately expressing what's going on in the situation. If I leave out the time interval, well, it turns out there's a lot of different changes in position. This is only one. There's the one from 0 to 0.8. So the moral here is be specific, be specific. Then the third thing is we need to give a basic meaning here. Displacement is the preferred technical term, but you can always, 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 always interpret the integral as the net change in whatever, in the net change in the antiderivative. That's the easiest way to think about it. So since velocity is the derivative of position, adding up the rate of change in position, accumulating the rate of change in position, automatically, fundamental theorem gives me the net change in position. Does that make sense? So that language works for any antiderivative, definite interval that you wish to represent. Is that better? I didn't answer one question. What about distance? Well, distance is tricky. For distance, we are looking at the total distance traveled, counting distance forward as positive and distance backward as positive as well. So for this particular trip, my distance traveled was 2 plus 5 is equal to 8. So let's work backwards and think about how we might, 2 plus 5 is 7. Thank you. See, we're all having bad days. And I was like, what's funny? Quick check, zippers up, yep. 2 plus 5 is 7. So, I got fooled by that. So the question then is, how should we represent the distance? Well, what we're doing is we are accumulating as we go, rate times time, but we're treating the rate as always positive. Oh, I know how to do that. I did that with absolute value. So the distance traveled would be the integral from 0 to 0.8 of the speed times time. Does that help? So distance really got 0 for that because actually the distance traveled is a different number because some of the displacement was negative. The best estimate for the distance traveled would be 3 times 0.2 plus 2 times 0.2 is 1. No, it's 0.5 plus another 0.8 times 0.2 plus 2 times 0.2 3.6. Yeah, that's right. And that's why it's so confusing, is that if you are dealing with only positive velocity, absolute value of v of t is v of t, so the distance traveled is the displacement if the velocity is all positive. And that's why people interchange the two so frequently. Because they're usually working in a reference frame in which they are going forward to the end. Okay, last question, what's the average velocity? Got to be very careful to distinguish between average velocity and average acceleration. Why are these different? Because I am given velocity, I would average that velocity by adding up velocities and dividing. Because I am given velocity, I would find the average rate of change of the velocity with a delta v over delta t. And so the question that you always have to look at when you see the word average is, are we looking for an average rate of change or an average value? And we will evaluate those two differently. Does that make sense? Okay, good. Well, I think that brings that to a close. Let's take a look at our lesson for today. We're going to be looking at what happens when you do definite integration using the fundamental theorem with a substitution or change in variable. At this point, though, who needs to wake up? The banana juice isn't working. You need something stronger. Try papaya. And so I want to consider some possible intervals here. I want to consider an easy one. So, and the mechanics here are not difficult, but you have to be careful. We have two different similar ways of carrying out this integral. One is by doing formal substitution, and the other is by doing repair, right? And both of those ways are conceptually the same, but they are different in terms of the paperwork. The formal substitution, I will say u equals blah, 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 and I will actually rewrite the integral in terms of u. With repair, I will do all that substitution work mentally, and I'll end up with an antiderivative in terms of x. This matters because these limits right here are values of x. I am saying integrate from x equals 0 to x equals 3. So that if I pull off the formal substitution, I will need to replace those values in terms of the corresponding values of v. That's the key. Let's do this by repair first because it's the easiest. If I do this by repair, then I'm integrating x plus 1 to the 1/2 power. Inside is x plus 1. du is dx. I'm right there. So I can just raise this with the power rule and get 2/3 x plus 1 to the 3/2. And now I can evaluate this directly from x equals 0 to x equals 3, which is going to give me 2/3 of root 4 minus 2/3 of root 1, which is going to give me 4/3 minus 2/3 for 2/3. Easy peasy, no problem. But if I pull off the formal substitution, things change a little bit. If I let u equal x plus 1, so that du is equal to dx, I now go through the process of rewriting my integral in terms of u. And that process we know how to do in terms of the integrand right here. But the other piece of it is that I need to also replace x values here with corresponding u values right here. And they're easy to compute. Since u is equal to x plus 1, I can evaluate u when x is equal to 0. I can evaluate u when x is equal to 3. So that I get an integral from u equals 1 to u equals 4 of root u du. Before we actually carry out the integration, I want to observe what we did here. The original integral took the function y equals root x plus 1, and it integrated that function from x equals 0 out to x equals 3, giving us this net signed area right there. Now, the new integral in terms of u takes a different function, the square root of u, which looks a whole lot like the old function in this case. And instead of integrating from 0 to 3, it now integrates from 1 to 4, which just happens to be the same region shifted over by that. If I were to integrate from 0 to 3, I would integrate a region with a different area. Now, the new region, the new substituted region, and the old region do not always have the same shape, but they will always have the same area. Does that make sense? Okay. Now, here's the payout. Having substituted here, I can now draw a mental line right here and ignore the old integral. Because I am now confronted with a new integral whose value is the same as the old one, And so as soon as I compute that, which is 2/3 u to the 3/2, from 1 to 4, then I get 2/3 of root 4. This is 4 to the 3/2, isn't it? Dang, twice in a row. Cubed, cubed, this is wrong. This guy should be 2/3 of 8 minus 2/3 of 1, which should be 16 14/3. And this guy also should be 4 to the 3/2 minus 2/3 of 1 to the 3/2, which is 14/3 as well. You noticed that, didn't you? You just let me go. Like the people that let you see your friend and they've got chocolate in their face, and you're like, I wonder how long it'll take them. So the key here is that my integral must always be in terms of x's or u's, but not both together. And so in particular, you remember last year I fussed with some of you because you would write mixed forms.
And I got it. I didn't even know all of this existed.
And it made sense, isn't it? Right? Yeah. Yep. Well, let's come back, and what I want to do is to show you the power of this when you get to the trig substitutions. Because the integrals involving trig substitution were some of our nemesis, right? They were pretty awful. When I'm doing definite integrals with trig substitution, something wonderful happens. So let's see that happen. Let's find the integral from -1 to 1 of root 1 minus x squared dx. Okay? I think we agree. Yes, that's right. First check if it's an odd function. It turns out it's not an odd function, so this integral sadly is not zero. It is even. So I could, if I wanted to, actually rewrite this like this. I approve. Good job. Okay. Now, next thing. This looks like a good candidate for trig substitution because it has a form a squared minus x squared on the inside there. So I should probably let x equal what? Sine theta.
Yes, there you go.
Yep. So we're going to let x equal sine theta. And when we let x equal sine theta, then we know this part of the integral is going to transform to cosine theta. And this part of the integral is going to transform to cosine theta d theta. And now, this part right here, the limits are going to transform as well. So we need to figure out the new limits. When x is equal to 0, that means that sine theta is equal to 0, so that theta is equal to 0. That's my lower limit of integration. When x is equal to 1, that means that sine theta is equal to 1, so theta is going to be equal to pi over 2. Just like that. Yes, sir?
What if there's 2?
That's a great question. Because I am working in the first quadrant here, where x equals 1, y is equal to 0, I'm going to treat, I'm going to take the principal value. But that's a really good question. So now what do I have? Now what I have is a new integral. I can draw a mental line right here and just evaluate this integral without ever having to back substitute. Remember that one of the things we didn't like so well about the trig substitution was having to take and put the original integral back in terms of x. We don't have to worry about that. So I now have 2 times the integral from 0 to pi over 2 cosine squared theta d theta. What's my approach for cosine squared theta? That's right, I do need an identity.
One minus
What's that?
one minus x.
Well, yeah, but that doesn't really help me much. Good, good, right. So she's trying to remember it, and this is the place to start. Keep going with that thought. You do, but what could you do about that? But you've still got science squared theta hanging out. We want to get rid of it. One minus cosine squared. Because the two have to add up to one, right? Okay, simplify that. Go.
Cosine squared theta minus 1 plus cosine squared theta.
Which is? Now, solve for cosine squared theta. Everybody has to walk through this because you are going to continue to see the integral of cosine squared. The integral of sine squared also. Maybe those with thumbs. What's that? No, it's not. As they taught my elementary school daughters to say, is this a big problem or a little problem? No, it's not. So what is cosine squared theta equal to? Go. Yeah. And so now we can substitute. Good. Now something wonderful happens if you're willing to think a little bit graphically here. I want you to notice that for this particular integral, something really nice happens, and that is that the function y equals cosine 2 theta is a trig function with a period of pi, right? It starts at 1 and goes down to -1 and goes back up. If you examine the integral of cosine 2 theta on the interval from 0 to pi over 2, what do you notice? What happens? The net is 0, that's right. So this entire term is going to zero out when I integrate from 0 to 2 pi. And so the result is that I get 2 times the integral of 1/2 from 0 to pi over 2. And the result of that is that I get exactly pi over 2 as my integral. Now, some different directions to take this, because this is a cool result. We're always interested when we integrate something algebraic and get something trigonometric. Take a look at what we did. First thing that's interesting is we just discovered a possible formula for computing pi. I could estimate pi by using any number of rectangles that I choose to estimate this integral. And that value will now give me pi over 2. So pi is equal to exactly 2 times this interval right here, and there you go. And the second thing we wonder is, why should that interval be equal to pi over 2? So we start examining the function in question, which is root 1 minus x squared, and we realize, oh, of course, that's a semicircle with a center at 0 and a radius of 1. So of course its area is going to be 1/2 of pi r squared. If I had only thought ahead, I could have just put a function there. Okay? So the moral of this story is that with trigonometric substitution, we can replace the limits of integration and not have to worry about back substituting. Second moral of this story is we need to know the double angle identities because they keep on coming back to haunt us. And you can bet that they will be coming soon to do a quiz or test near you. So rather than try to fight it, say that's unfortunate, you just want to figure it out. And the key is to begin with your basic double angle identity and do a little bit of substituting out. In the spirit of that, at this time, I'd like for all of you to write sine squared theta in terms of the double angle identity. Don't guess, and work it out, and make sure that you're right. All right, John, tell me how it goes.
Sine through theta equals sine squared theta minus sine squared theta.
Why?
That's great.
Why? Where does it come from?
Double angle.
Are you sure?
I told you that is.
Okay.
So I just know it's a.
Actually, it's not. You're incorrect.
They flip it or something.
No, you have a completely incorrect identity entirely. The identities are not magical incantations that you memorize in order to level up. They are relationships between the trig functions that have to be understood as relationships. So we have to go all the way back to angle addition. We went through these proofs before, and all of you kind of, whatever. This is false. There are a couple of ways to see this. I have document in your folder in Edmodo that goes through proof. I'm going to do a slightly different proof. Let's see if I can do it in 3 minutes. This angle right here is going to be theta plus phi. And therefore, the coordinates of this point are cosine theta plus phi and sine theta plus phi. And what I'd like to do now is to compute the distance from this point, which is 1 comma 0, out to this point. And I'm going to compute it in 2 different ways. One is I'm going to use the Pythagorean theorem, and the other is I'm going to use the law of cosines. What's that?
Cosine, if you start with cosine 2 theta, and then you get cosine squared theta like that as well. Sine squared theta.
So what is cosine 2 theta equal to?
Cosine squared theta minus sine.
Yes, it is. Obviously can't be equal to sine 2 theta. Okay, now what?
And then you solve for so you get sine squared theta is equal to cosine squared theta minus
Yeah. Keep going.
Shouldn't that also be equal to sine squared theta? Like cosine.
Why?
That's what I'm asking. Like, there are 2 different things, right? Like sine squared is different than sine 2. Okay.
Certainly, yeah. So sine
So
squared
I
theta.
need them myself.
So sine squared theta means that you find this y coordinate here and you square it, right? Sine 2 theta means that you are going to go out to theta plus theta and find that y coordinate right there. And actually, since we're on the unit circle, you can see that sine squared theta has to be less than sine theta, because it's going to be a number less than 1. And sine 2 theta in the first quadrant is going to be a number larger than sine theta. All right, so this isn't really helping us. If I replace cosine 2 theta with cosine squared minus sine squared, I just find out that sine squared equals sine squared and that whole thing.
Yeah, I did that and I was like, well, okay.
All right, we need something helpful with this. We're looking for sine squared theta. Mm-hmm. Keep going. Mm-hmm. Yep. And there you go.
It's the same thing I got using the backwards one.
No. You had something really weird.
But I guess that's.
Wow. You got sine 2 theta.
Oh, it's sine. We have the same thing, so it's different.
Yeah. Not the same at all. I'm going to turn the recording